All right, in this penultimate video of Calc 1, or at least topic, who knows how many videos there'll be for our last topic, what I want to talk about is just some basic quick results that we can get from our definition of definite integrals and the fundamental theorem of calculus. These are some pretty basic things that do show up in application, but I just want to kind of run through them quickly just so we get a basic idea of what's going on here. So first we're going to talk about symmetry of functions. We'll remind ourselves about what that even means, and then we'll see how we can use symmetry in our integrals to make our lives a little bit easier. Then we're going to take a look at the average value of a function, and from there we'll be able to build the mean value theorem for integrals, which is pretty much a direct extension of the mean value theorem and our definition of definite integrals in the fundamental theorem of calculus. So here we go. We'll first start with this idea of symmetry here. We're going to talk about even symmetry, we'll talk about odd symmetry, but first here's our quick reminder. These are our definitions of symmetry. A function is even symmetric if f of negative x equals f of x for all values of x. So our classic example might be like a parabola, right? This x squared function. Where if you have some sort of a positive x value here, we get x squared for the y value, and if you look at a negative x value, when we square it, it still becomes positive. It's the same y value, right? The main idea here is that when you square a positive or a negative version of a number, it's the same answer. So that's what even symmetric is all talking about. Our other classic example of even symmetry is the cosine function. Our cosine function is even symmetric. We might think graphically that even symmetry is like a reflection across the y-axis here. But another thing that we can notice is that if we look at the unit circle and we think about our cosine function, ooh, that's pretty bad. Let me fix that. There, this is better. And we look at some value of theta. So we're going to think about cosine of theta, where this is our angle. I'll get a straight line here. This is our angle theta. Well, remember that cosine theta is the x value, of this point. And so if you look at negative theta, that's going to be some negative angle, but the same kind of measure, right? The same absolute value, the same size of the angle. So negative theta is going to be right here, and we should be able to see pretty easily that these have the same x value. And so they're going to have the same value for cosine. So, cool, even symmetry, we've got it. Odd symmetry is when f of negative x equals negative f of x, or sometimes you'll see it written like this, f of x equals negative f of negative x. Same thing. For all x values, you can think of a nice odd degree power function. Maybe we'll take a look at like a cubic function that looks something like this. Oh, that's pretty bad. Let me fix this. Oh no. Let me just do this over again. All right, that's a little better. That's better. Okay. And then we could look at some x value here and some negative x value here. And you'll notice that they have different coordinates, right? But the coordinates are actually just opposites of each other. So this would be x cubed and this would be negative x cubed. The main idea is that with this cubic function, it preserves the sign, right? So negative 2 cubed is negative 8. That's the same thing as negative of the 2 cubed. So same thing. And then our trig function example is our sine function. Oh no. There we go. Our sine function looks like this. And so you might think of it as like a rotation around the origin. And if we go back to this unit circle idea, we can hopefully see pretty easily why our sine function is symmetric. We're going to do the same kind of thing that we did earlier. We're going to take a look at these 2 points with an angle theta and negative theta. So here's our angle positive theta, and here comes our angle negative theta. I'll try and draw that in a little bit here. Theta. Well, that's a bad theta. There we go. That's a little better. Not much better. Oh well. And we'll remember that our sine of theta is the y value of this coordinate. And hopefully we can see that the y values are reflected. So I'll just get rid of that, actually. Hopefully you can see the y value of the red point is negative of the y value of the blue point. So we've got this nice odd symmetry. Cool. All right, so how does this impact our integrals? Well, we'll try and keep in mind that what an integral really is an accumulation of y values, right? We're adding up all of these things, and it's almost like that's where this idea of Riemann sums comes from, right? We're adding up all these areas of rectangles, and now here we're accumulating, we're adding up, we're summing. That's why this integral sign looks like an elongated S. We're summing up all of these values. And so if you have an even symmetric function going from negative a up to a, meaning we're kind of straddling, the origin here, then let's just take a look at our even symmetric function. I'll grab a parabola because it's going to be a nice easy one to draw. But you could draw any even symmetric function here. And if you look at the integral from negative a up to a, then hopefully we can see that these two red regions are equal to each other, right? They're going to have the same size. Clearly they have the same width. They're going from 0 up to a or from negative a up to 0. But that's a width of a, whatever that value is. And they're going to clearly have the same kinds of heights at all the points because of this even symmetry. And so hopefully we can see that this is just half of the total, or you can say the total is 2 times that side. So the integral from negative a to a is equal to twice the integral from 0 to a. Why is this useful? Well, maybe it's easy to integrate things and evaluate antiderivatives at 0 sometimes. More helpful, I think, is this nice odd symmetric thing. Because with odd symmetry, if we draw a nice odd symmetric function, maybe I'll do a cube root one this time just to get a little crazy. Here, out to here, you can hopefully see that from negative a up to a, if we look at these regions here and we shade in areas, these are the same size, but one of them is positive and one of them is negative. And so when they add up, hopefully we can tell that they're going to be adding up to 0. This is going to come right from our definition of even and odd symmetry. If you try and figure out what's going to happen with evaluating antiderivatives and all that kind of stuff, things work out really nicely there. All right, so that works out fine. Let's use this for a couple of examples. Here are some basic ones that shouldn't require us to do too much thinking. The main thing that we're going to do is to just split these up first into just one-term integrals with power functions, because then we can say, all right, I can look at this first one and say that's odd. So I know this thing is equal to 0. And this one is even. So I can say this is going to be 2 times the integral from 0 to 4 of x squared dx. Now the reason I might do that is because I can just do the rest of this in my head now. I know that the antiderivative of x squared is x cubed over 3. I know I'm going to evaluate that at 4 and 0. Evaluating it at 4 is 4 cubed over 3. I'll figure out what that is in a second. But notice, evaluating at 0 is super easy. It's just 0. So this ends up just being 2 times 4 cubed over 3, and we don't have to do anything more. 4 cubed is 64, so we're looking at 2 times 64 over 3. What's that, 128 over 3? I just shortened down the amount of arithmetic I had to do here. Sometimes that's helpful, sometimes not, but in some applications it's really useful to be able to do something like this, and you'll see that later on. We can do the same kind of thing with this second example. We can break this up into 2 integrals. Looks like I forgot a little differential here when I was typing this up. Whoops. So we can split this up into 2 integrals. One from negative pi over 2 to pi over 2 of our cosine function dx. And then we have from negative pi over 2 to pi over 2 of 4 sine cubed x dx. And we might be noticing that there's a bit of a problem. I know the antiderivative of the cosine function. It's negative sine of x. I know the antiderivative of the sine function. Oops, sorry. The antiderivative of the cosine function is just positive sine of x. The antiderivative of the sine function is negative cosine x. But I do not know, right now at least, the antiderivative of sine cubed. That's a completely different thing. And we're going to learn later that that's a little harder than just saying, well, it's probably the antiderivative cubed. It's not that. We're going to have to do a little bit of work on something like this, which can be frustrating and difficult. But what we'll notice is that sine of x is an odd symmetric function. And so sine of x cubed is still odd. And so this thing is just 0. Cool. So all I have to do is say we're left with 2 times our integral from 0 to pi over 4 of cosine x dx. And again, evaluating at, it's supposed to be a negative here. It looks like it got wrapped up in the pi. Looking at the sine function evaluated at 0 is really easy. So this is going to be 2 times sine of x evaluated at pi over 4. Because we're really going to subtract sine 0, but that's just 0. And then you could go from here. So we end up with root 2. Cool. So these properties will hopefully make things a little bit easier. Just as a practice problem, let's take a look at this example. Let's say that we know that we have some function that's odd symmetric, and we're given 2 integrals. We're given 2 areas, really, that we're looking at. This is sometimes a hard type of example to work with, but let's go ahead and, I'm going to move this over actually. Let's go ahead and just draw this thing out. Let's draw an odd symmetric function. Doesn't have to really be anything special, but if we draw it carefully, we'll be able to draw it kind of to scale. I'm not going to even worry about that though. I know that I need to look at -3, -2, -1, and then 1, 2, 3, and I'm not going really further than that. I know that I have this area from -3 to 1, that's 4. I do have an odd symmetric function, so I need to have some sort of rotational symmetry on here. Again, I'm not really going to care too much about the actual areas, so what I might do is just draw some function that looks like this. Now what you're going to notice is that this is going to clearly not be the right function, but that's not what I'm really looking for. I'm just looking to carve in here and say this shaded in red stuff as a net area, that's 4. And then I also know that this green stuff from 2 to 3 is 1. Now, again, my picture's wrong. Really, there would be a bunch of oscillation in here. But we're not doing this to get an accurate picture. We're doing this so that we can see a little bit about what's going on here. I know that this total area that I'm going to shade, including this stuff here in blue, I know that this total area has to be 0, right? Because we have this nice odd symmetric function. And so if the total area is 0, what I can do is say, all right, that means the area from -3 to 3 of f of x is 0. But what this really is the sum of all 3 of these areas, right? We can use that nice little midpoint property that says you can cut up an integral into portions and then just string them all together. So I've really got all 3 of these integrals, and I know what 2 of them are. I know this one's 4. I know this one's 1. And so I should be able to figure out what this is, because I know that this all has to add up to 0. So 0 is equal to 5 plus something. We've got that our integral here, this blue stuff, that better be -5. So we can use this symmetry really nicely to find areas that we don't know by stringing together some stuff with areas that we do know. So getting a picture, I think, is always helpful. Trying to visualize what this looks like, even though this picture is wrong, right? I've got this green area underneath the x-axis, but I'm saying that it's +1. That's kind of fine here. I'm not looking at this sketch trying to get an accurate sketch of f. I'm looking at it to try and figure out how these things are going to work together, how these areas are going to combine together for this odd symmetric function. Okay, a new topic not related to symmetry. We're going to talk about the average value of a function, and maybe you're looking at this saying, why does he have a picture of some sort of a cup of water, a crappy clip art of a cup of water here? What I want you to do is to just kind of hang with me for this little thought experiment. If you want to try it at home, you can, although be careful, you might spill. We're going to imagine this cup of water that I've kind of shaken up, stirred up a little bit, and then I've slammed down on a counter or something like that, and then we kind of paused. And this is what we're looking at. See how the water's sloshing around? Well, it's in the middle of sloshing around and we've stopped it. So what we want to do is just imagine what's going to happen to the water if we leave our cup there and let it slosh around for a while. Like, what happens if we hit play on this? Hopefully it's pretty obvious that the water is going to level out, right? If this is sitting on a flat surface, on a level surface, then eventually our water level is going to become almost flat. It'll be something like, oh, maybe not there. Maybe up here. Oh, even worse. That looks okay to me. I'm drawing this blue line. What I want you to think is, first, how did I know that my first 2 attempts at this were not good? How did I realize that this was not going to be where the water level leveled out? And this might not be perfect, this version, but how do you know that it's relatively good? What are you looking at, or what was I looking at, to try and see if this is a reasonable line to draw? I've done this activity in class, and almost every time I get students that get a really, really accurate spot on here, a really, really accurate reading of where to put this horizontal line, right? They're really good at directing me and saying, no, that was too low, go a little bit higher, oh, that's too high, go back down a little bit more, okay, that's perfect. How do we know this? What are we really looking at? Most of the time, students have the same answer. They say, I'm just trying to look at how much water was above the line and compare that to how much empty space is below the line. And if I can make those 2 regions match up, that's going to be the height at which my water levels out. Seems reasonable, right? First off, I always think this is a pretty incredible thing that we're able to just eyeball and do, right? That seems, I don't know, interesting. I'm not a biologist or a psychologist or anything like that, so I have no idea what's actually going on in the human brain when we do this. But we're pretty good at picking that spot by balancing those areas. What we can do now is the same thing. We're going to say we have some function and we have an interval between a and b, and we want to find the average value of the function on this interval. Or we want to figure out where is that water level going, right? And again, we'll do it in the same way. We'll try and balance out areas. So this is clearly too high, because we've got this area up here that's really small and this area under here that's really big. So we'll probably bring this down, maybe there, but I think I might want to go a little lower. I think that looks okay. That's good enough for me. And again, I'm comparing this red region with this one. These are different shapes, and so it is difficult to compare areas. I know I'm not in the right spot here, but at least it's kind of close-ish, right? We're still good at comparing the sizes of these without having to be too specific. Okay, so what I want us to do then is to follow this logic. I'm going to draw a green box. Maybe I'll make my lines a little thicker so you can see them a little bit better. There we go. Here's a green box. And what we're saying is that the red areas, these 2 things, I'm going to go back to a small thing here. These have equal areas. All right. So if we want to find the height of this green rectangle, that's really what we're looking for average height here. So that's going to be something that we'll have to figure out. The way that we'll do that is by saying area of this box is equal to base times height. So that means that height, is equal to the area of the box divided by the width of the base. And I know both of those things, kind of. Here, b minus a is my width. And now, if only I could come up with some way of finding area of the box. What we'll notice is that if I've drawn this green height of my box in the right spot, if these two red regions actually do have equal area, then the area of my box is exactly equal to the integral from a to b of f of x dx. This blue area is the exact same thing as the area of the green box. So, all this to say, if you want to find the average height of a function, this green bar that we have, take the area, which is the integral, and divide it by the width, which is the difference of b minus a. And that gives us the average value of our function. So here is that average value of the function written out. If we have a function that's integrable on the interval from a to b, then the average value of that function, or sometimes we'll think of it as the average height of the function on that interval, we'll commonly denote it as f bar. You may have seen that notation in statistics, is the integral divided by the width, or you can factor out that fraction, 1 over b minus a, times our integral, f of x dx. So that's how we might find the average value of a function on some sort of an integral. Directly related to that, then, is this mean value theorem for integrals. If we have a function f that's continuous on an interval from a to b, then there's going to exist some point in that interval where the height of our point is equal to the average height, right? Remember what this is. This is just average height. So let me draw that for you so you can see, oh, okay, yeah, this is going to make some sense, right? This visually feels like it should work, and then I'll show you a lead-in to the proof of it. That'll be all we really need. So we're going to draw that same sort of picture for us. Here's our interval from a to b. We're going to look for an average height. I'll draw it in red. I'm not going to be too picky about where it is. All this is saying is that there is going to be a point right here in this case where they cross. So here's c, where f of c, the height of the function, is exactly equal to the average height of our integral. As long as your function is continuous, that's going to be true. This is actually a really easy thing to show, because what this is that f of c is equal to this integral from a to b of f of x dx divided by b minus a. But based on the fundamental theorem of calculus, this is capital f of b minus capital f of a over b minus a. And doesn't this kind of look like our mean value theorem? This thing here is equal to this thing here, especially when you notice the relationship between little f and big F. Little f is big F prime, right? Big F is an antiderivative. So this is exactly the mean value theorem, just restated and repackaged using integrals instead. So there's really nothing new about that. That's all that we've got for this video. Hopefully that's helpful to see those couple of properties of definite integrals that we can think about.